Today we are going to derive Wien's displacement law. Wien's displacement law from Planck's radiation law. Planck's radiation law. Okay, so let us see here. So what I'm taking initially Planck's radiation law. We know very well that E lambda d lambda equal to 8 pi hc by lambda to the power of 5 d. Arey! Yava! Close the door. Go. Tikama on the Uluta on the. Stop it. D lambda by e to the power of hc by lambda kt and the minus 1. So this is what Planck's radiation law, what we deduced in the last class. Okay. Now, so with the help of this equation, so we'll write E lambda equal to, this can also be written as 8 pi hc by lambda to the power of 5, so 1 by e to the power of hc by lambda kt minus 1. Okay, now so let us assume this is constant value, that is represented by capital A. Then we'll write E lambda is equal to A into lambda to the power of minus 5, and so e to the power of hc by lambda kt minus 1 whole to the power of minus 1. Okay, now so let us differentiate this equation with respect to lambda for maximum wavelength. Okay, differentiate above equation with respect to lambda for maximum wavelength. So therefore, see what we get there. So here initially you must know that then the differentiation of x to the power of n, then the differentiation with respect to x to the power of n can also be written as, you know that this is one formula. So differentiation of x to the power of n with respect to x can be written as n into x to the power of n minus 1. Alright, so using this formula, let us see how can we derive this equation. Now the differentiation of this above equation can be with respect to lambda can be written as d e lambda by d lambda equal to 0. So we'll get maximum value to get maximum wavelength, and then the differentiation of this equation with respect to lambda can be equal to 0. Alright, so then what we get there, if we differentiate this one, you know very well that A remains constant, let us write outside, A remains constant, let us write outside, then and UV method, let us apply XY method. So lambda to the power of minus 5 remains same, don't change that one, and differentiation of, let us assume this is x, if differentiation of this one can be written as minus 1 into and e to the power of hc by lambda kt minus 1 whole to the power of, here this can be minus 1, that can be become minus 2. And now the differentiation of this bracket function, the differentiation of this one can be what we get there, e to the power of x is differentiation of e to the power of x can be written as e to the power of x, then we'll write e to the power of hc by lambda kt, and again differentiation of this power term, so that can be, if we differentiate this one, what we get there, e to the power of hc by lambda kt, and so differentiation of this term can be hc by kt remains same, and 1 by lambda can be written as minus 1 by lambda square. Then finally we'll get there minus hc by lambda square kt. Okay, lambda square kt, and here it is. So now the differentiation of this one can be minus 5 into lambda to the power of minus 6, and the bracket term remains same. So here we'll write e to the power of hc by lambda kt minus 1. So that is equal to 0. Okay, that is equal to 0. So this is what a differentiation of differentiation of this equation. Okay, now so here from this equation let us take common. So that is what, here we have -1. So that is what I'm taking common e to the power of hc by lambda kt, and lambda kt -1 whole to the power of -1 common. Then what we get there, and you know that a is constant, so that is equal, that is sent to the right side, then it will become 0. And then finally if you take this term common, what term is remains same here, e to the power of hc, e to the power of hc by lambda kt, and lambda kt into e to the power of h by lambda kt into hc by lambda kt. Okay, so here what we get there finally, so this is the term, and what I'm taking this term common, e to the power of st by lambda kt -1 taking common. And then what happened here, if you take this one common, and what is there remain here, so here it is, what we get there, if you take that common, here we have the term minus here, minus into minus plus this one here minus, we have the term 5, and lambda to the power of -6 is there. Here we have one more term, lambda to the power of -5, so that equal to 0. And here also we have one more term, so that is what, so all right, here we know that e to the power of hc by lambda kt -1 whole to the power of -1 common. If you take that common, and a into e to the power of hc by lambda kt -1 to the power of -1 becomes 0, and the remaining what is there, here we have the term e to the power of hc by lambda kt -1 whole to the power of -1 remains same. So next, so e to the power of hc by lambda kt and into hc by lambda square kt, right, lambda square kt into lambda to the power of -5, which remains same, and -5 into lambda to the power of -6. So that means what happened here, only this term, so this term and this term from this term taking common and sending to equal to 0, and remaining term is this one. Now let us see here, so from this equation what we get here, so from that equation, so finally we'll get there. What is that, here we have e to the power of hc by lambda kt -1 whole to the power of -1, and into e to the power of hc by lambda kt into hc by lambda square kt. So that equal to, here we have the term, here we have a lambda to the power of -5, and that is equal to 5 into lambda to the power of -6, and we know that this one and this one cancel, and finally we have the term hc by lambda square. Here it is, you know that hc by lambda square kt, hc by lambda square kt, and e to the power of hc by lambda kt by e to the power of hc by lambda kt -1, so that equal to 5 by lambda. So we know that this one cancel, and finally we have the term hc by lambda kt, and so we have the term e to the power of hc by lambda kt by e to the power of hc by lambda kt -1, so that equal to 5. So you know that this equation is in the form of x into e to the power of x by, so e to the power of x -1 equal to 5. So from this equation, so we know very well that this can also be written as take e to the power of x common and cancel, so finally we have the term x by, so 1 minus e to the power of x equal to 5. So finally here it is, we'll write x equal to 5 minus 5 into e to the power of -x. So from this equation, again this can also be written as x by 5 plus e to the power of -x equal to 1. Okay, so here, so we know that here x equal to what, x is equal to hc by lambda kt. All right, here x equal hc by lambda kt. All right, so from this equation it has two roots. This equation has two roots, so that may be x equals 0 and x equal to 4.965. So this equation has two roots, x equals 0 and x equal 4.955, sorry, 55. All right, so now we know that what is x value. X value is equal to x equal to hc by lambda kt, and that equal to, here we'll write 4.955. so from this equation we know that where h is Planck's constant, that is constant 6.625 into 10 to the power of minus 34 joule second, and where 6c is nothing but light velocity 3 into 10 to the power of 8 meter per second, and where k is Boltzmann constant. So from all these in this term we know that where h, c, k are constants, but lambda t are variables. So then we'll write this equation as lambda t for maximum. So lambda maximum t equal to, so constant, that can be written as b. All right, so this is what Wien's displacement law, lambda t equal to constant, Wien's displacement law from Planck's radiation law. So this is resolved. And one more thing, we have to see the Stephen's Boltzmann law. Stephen Boltzmann law. So what we get there from this here, from Planck's radiation law, we are going to derive Stephen's law. We know that sigma equal to sigma Stephen Boltzmann law, where E equal to sigma t to the power of 4. So that one we are going to derive here. We know that according to Planck's law, so in terms of frequencies, E nu d nu equal to, so E nu d nu equal to 8 pi h nu cube by c cube into d nu by, so exponential, that means e to the power of h nu by kt and minus 1. So this is what Planck's radiation law in terms of frequency. So in terms of frequency here, now what I am going to do here, the spectral intensity E nu spectral is related to energy density E nu, which is related to energy density E nu. So we know that relation can be written as here. So E nu spectral equal to C by 4 E nu. Here E nu spectral d nu. So that means what I am doing, E nu spectral d nu equal to C by 4, so E nu d nu. So what is E nu d nu? We know that one. Substitute in this equation. So C by 4 into here 8 pi h nu cube by c cube, 8 pi h nu cube by c cube into d nu by, so exponential h nu by kt minus 1. All right, so here we know that 4 1 4 2 and c here, so it cut down, then we'll get there 2 pi, so h nu cube by c square into, so d nu by exponential, that means e to the power of h nu by kt and minus 1. All right, so total radiant energy. So how can we get total radiant energy? Here total radiant energy E can be written as E equal to integral 0 to infinity and E nu spectral d nu. Now substitute this one here, then finally we'll get there E equal to, after substituting we know that this whole thing is constant right outside, then what we get there, 2 pi h by c square and integral 0 to infinity nu cube and d nu by, so e to the power of h nu by kt minus 1. All right, so this is formula, and let here h nu by kt equal to x. I'm assuming h nu by kt equal to x. Now from this equation nu equal to, so kt by h into x, and differentiating this one, what we get there, d nu equal to kt by h into dx. So now substitute here nu value and d nu value in above equation here. So then what we get there, finally if you substitute in the above equation these two nu and d nu values, then finally we'll get there so finally we'll get there here E equal to 2 pi, so h 2 pi h, right, 2 pi h by c square, so 0 to infinity and the nu cube So nu cube, in place of nu cube, we have to write kt by h into x whole cube by, so here I'm writing e to the power of x minus 1 into d nu value. What is that d nu value? So kt by h into dx. So with this equation we know that here h cancel, and finally we have 2 pi. So here we'll write kt to the power of 4 by, here I'm writing h cube into c square, and 0 to infinitive x cube dx by e to the power of x minus 1. So this term can be written as here, this term can be, we know that is one formula, so that is equal to 2 pi kt to the power of 4 by, here I am writing h cube and c square into, so this is equal to the formula pi to the power of 4 by 15. All right, so from whole this thing, so we'll get there. Simply we can write this one as where 2 pi k h c all are constants, so we'll write this equation completely equal to sigma into t to the power of 4. So that is what Stephen's constant, this is what Stephen Boltzmann's law, where E is directly proportional to t to the power of 4, and where sigma equal to, we'll write 2 into pi to the power of 5 and k to the power of 4 by, so 15 into h cube and c square. So this is our required equation equal to sigma into t to the power of 4. So here what we done there, we derived Stephen's Boltzmann's law from Planck's radiation law. All right.